Hello everyone. I hope everyone is having an amazing time over there and you guys are continuing your physics revision, right? And today we are going to continue our live discussion for AIATS plus phase 2 mock test 6, which was conducted on 23rd of February this month. Okay, and let's see what are today's topics, which are pretty much we are going to continue from where we left off last week. All right. So these are the topics of today. We are going to be beginning with work, energy and power, and as you guys already know, we have done so many problems of work already, right? And if you remember last time we were discussing about springs as well, right? A beautiful question I had also given you as homework as also. So let's see. Let's see what the question is. Read the question. A spring of force constant. So force constant is given to you. Okay. 500 Newton meter has an extension of 4 centimeter, right? So force constant implies your K. Okay. So the moment you read the question, this symbol has to pop up in your mind. And extension that means the symbol X that we generally use, right? So initially the extension is 4 centimeter. Now what are they asking? Find the work done in extending it from 4 centimeter to 12 centimeter. So what we have done, see, if I have pulled this spring like this, so I've already pulled it, right? I've already pulled it by 4 centimeter, and now I'm extending it even more. That means the extension increases from 4 to 12. Let's see it in a diagram. So if you see over here, this was the original condition, right? So let's say this is original. Originally, the spring was in this configuration. So no pulling or no compressing. But now what I am doing, I am pulling it. So see, like this. I am pulling it by some distance, let's say 4 centimeter, right? And just for some revision, pulling it by 4 centimeter, that means the displacement is in which direction? The displacement will be towards right. But what about the restoring force of the spring? The spring is also going to apply a force, right? Spring force. And that will be in what direction? It is towards left. Why? Why so? Because the spring wants to, you can remember it like this, the spring wants to return to its original dimensions. Okay. So which means the original dimension was over here, right? That's what I told you. Or we can also write it over here, original natural length. Okay, so it wants to return. So if a spring force is always directed towards the original position. Okay, so if you see, the displacement is towards right, but the spring force is towards left. Likewise, in the opposite case as well, right? So let's say if I had compressed the spring, right? Or let's say the block is on the left, that means the displacement is towards left. But what about the spring force now? The spring force will be towards right, isn't it? Because this is the equilibrium position. The spring wants to return to here. Okay, so spring force is towards right, displacement is towards left, which is why we can conclude it as like this. Okay, so the F is always opposed to your X. If you want, I can write over here the spring force, okay, it is equal to minus of Kx vector. All right, now speaking of the question, as it had been said, it has been elongated by X. So there would be some energy that would be stored in the spring. That energy is called elastic potential energy. Okay, and that energy expression goes as half k x square. Okay, very simple formula. You need to remember this, half k x square. Yeah, good afternoon, Aman. So coming back to the question, as you can see, initially it had an extension, right? Which means initially it had an energy in the spring. So let me write it as Ui. And Ui is how much? Half k into 4 centimeter square. 4 centimeter is 4 upon 100 meter, right? So I can write it as, let's say, 4 by 100, half k x square. Now finally what is the extension? From 4 centimeter it is going to 12 centimeter, right? So final extension or the final potential energy stored in the spring would be half k 12 by 100 square. Okay, and what are they asking? They are asking the work done in this process, right? The work done, and who is doing this work, by the way? We are the ones who are doing it, right? We are trying to pull the spring towards right, isn't it? We are pulling the spring towards right, okay, and the restoring force is towards left. So anyway, the work done, we can write it as, okay, U final minus U initial. Now that's it. Simple calculations now. You just have to subtract them, right? Half k, you can take it as common, right? And this 100 square is in the denominator. That also you can take it as common, okay? 100 square. So what remains? UF minus UI, 12 square minus 4 square, okay? So 12 square minus 4 square. So I put the value of k as well. K is how much? 500, right? So half into 500 upon 100 into 100, okay? 100 into 100. And this is how much? This is how much? I can write it as a square minus b square, a minus b into a plus b, right? So 12 minus 4 into 12 plus 4. 12 minus 4 is how much? 8. 12 plus 4 is how much? 16. Okay? 12 minus 4 into 12 plus 4. You just have to cancel the terms now. See, these get cancelled. Then 5 and 100 become 20. Okay, then 2 and 2, 4. 4 you can cancel out with 8 over here. So it is 2. So 2 into 16 by 10. 2 into 16, 32 by 10. Okay, 32 by 10. And the unit would be in, what's the unit? Joule, isn't it? So the answer would be 3.2 joule over here. Okay, this was very easy, isn't it? Let's do a similar question, just like this one. See, this one you would be finding it very easy now. See here, literally the same question, right? Initially, if you see, the work done in extending a spring by L naught is W naught. Okay, by L naught extension, work done is W naught. So the elastic potential energy in the spring would be half k L naught square, and that work done gets stored as elastic potential energy. You can remember it as in this manner as well. Okay, and the work done, they're asking the work done in further extension of the spring by I naught. Okay, the further extension is L naught. Okay, L naught. So for further extension, what will be the work done? Just now I told you, UF minus U initial, right? So half k, what is finally, what will be the total extension? L naught plus L naught. So it is 2 L naught, isn't it? Let me write like this, 2 L naught whole square, finally, minus initially. So initially it was L naught only, right? Just like the last one, right? Exactly what we did over here. Half k final square minus initial square. 2 L naught square minus L naught square, okay? This is 4 L naught square minus L naught square, 3 L naught square, 3 L naught square, right? So I can write 3 into half k L naught square, and that is nothing but 3 W naught. It was a very basic question, this one, isn't it? So the correct answer would be 3 W naught. All right. So okay, so let's move to the next topic, gravitation, right? And if you remember last time we had done some derivation as well, isn't it? For gravitation, variation of acceleration due to gravity with and its dependence on the radius of the planet and density of the planet. This we have done. And if you see the same question, almost pretty much the same, see, acceleration due to gravity on the surface of Earth is g. On the surface of Earth is g. Okay, so this is given. Then acceleration due to gravity on the surface of another planet of same density but radius half of that of Earth. Okay, yeah, good afternoon Ronak. So same density, meaning the density of planet, let's say rho dash, is equal to density of Earth, but the radius of planet is half, right? So radius of planet, let's say r dash, what is it? Half that of Earth, okay? Half of Earth. And what was the relation that we had derived? If you remember, the how does g, acceleration due to gravity, depend on density and radius? If you remember, we had derived this one, right? G is proportional to rho into R. Okay, so whenever they talk about density, you can use this expression, rho into R. How did we get this? If you want, we can recapitulate once again. A small recapitulation. Okay, so let's say I'm talking about Earth only for now. I'm only talking about Earth. So what would be acceleration due to gravity on the surface of Earth? Right. So this, remember, we are writing for Earth. Revision. So G is equal to Gm by R square. Right. Gm by R square, where this capital M, what is it? This is mass of Earth, capital R, this is the radius of Earth. Okay, but from now on I will only write it as capital M and capital R. Anyway, and this capital M, what can you express it as in terms of density? Because as I said, we are trying to find the relation of G with density. So this mass can be written as what? Density into volume, right? Density is mass by volume. So mass is density into volume. And you substitute it over here. So this becomes G, mass is what? Density into volume. Density into volume. Volume. What is the volume of Earth? It is a perfect square. We assume it as. So it becomes 4 by 3 pi R cube upon R square. Okay, and you just cancel the terms. R square and R cube will get cancelled. So what remains? See over here, 4 by 3 rho G pi as well with R, right, with R. So which is why I had written over there G is proportional to rho into R. So if you remember this, there is no need to derive. Okay, so please remember, see why rho into R? See, all other are constant, 4, 3, pi and capital G, they are all constants. So rho and R, they can vary. So rho into R. And come back to this question. So we are going to be using this relation, right? So how do we use it? Very simple, right? If you see over here, they have also said that density is constant. Just now I told you it can vary with density, but they have said density is also constant. That means you can simply write G is proportional to R. But density is also constant. Density of Earth and density of planet are same. So what will this become? See over here, very simple. G dash by G is equal to R dash by R. That's it. Very simple, right? R dash by R, and what is R dash? Half. So this is R by 2, right? Upon R, and this becomes 1 by 2. R get cancelled. So what will G dash become? Take this G over there. So the correct answer is G dash is equal to, okay? Yeah, thank you Puneet. G dash is equal to G by 2. So the correct answer would be option number 1. Okay? So it's a very simple question, this one was. Alright, we move on to the next question. Now read this question as well. The ratio of distances of two planets from the Sun is 9:1. So distances from the Sun is at the center. Let's say the planets are revolving in a, they've already said, right? Consider orbit of planet is circular. They're revolving in a circular orbit, and at the center of that orbit is your Sun. Okay, so revolving around the Sun. And what would that distance become? Distance is nothing but the radius of that orbit, isn't it? Sun is at the center. So we can say the ratio of distance is 9:1, right? So I can say, let's say R1 by R2, okay? R1 by R2 is how much? 9/1. This is given to you. What is the next they asking? The ratio of their time period of revolution will be, right? Around the Sun will be. So ratio of time period they are asking. That means T1 by T2 they are asking. Ratio of time period. Now how to do this question? This also we have done earlier, right? You need to remember Kepler's 3 laws, right? The moment you see time period with radius, etc., Kepler's 3rd law has to come to mind. So we can use T square proportional to R cube. That's all. You'll get your answer. T square proportional to R cube. Right? So just put it. What will this become? See over here. T1 by T2 whole square. The moment you see proportionality sign, you can directly start writing the ratios, right? So T1 by T2 whole square is equal to R1 by R2, what is the power? 3, right? So here you will write R1 by R2 whole cube. And what is R1 by R2 given over here? 9 upon 1. 9 upon 1 whole cube. What does that become? 9 into 9 into 9, right? So it is 9 cube only. 9 cube is what? 729, right? 9 into 9, 81 into 9, 729. And 729, you can write it as what exactly? You can write it as 27 into 27. Okay? That means it is 27 square. Nothing else. Okay? So this means this is 27 square. Okay? If you want, you can check it as well. Right? Which other numbers would satisfy such a thing? See, if you had 4 cube, right? Let's say if it was 4 cube, 4 cube can be written as 8 into 8, 64. 4 cube is 64, 8 into 8 is 64. Okay? Alright, anyway, so what will this become? T1 by T2 square is equal to 27 square. Isn't it? See this one, T1 by T2 square is equal to 27 square. So what will be T1 by T2? What will be T1 by T2? It would be nothing but, take square root both sides, this one and that one, 27 only, right? So what would be the ratio? We would say 27 is to 1. Okay? Very simple this one. We have already covered these topics, so it was would be good revision for you as you do these problems. Alright, moving on. And today under solids we are going to be starting a new topic for you guys, and again it's going to be recapitulation, right? If you remember, in solids we had done Hooke's law, right? And I have also drawn the stress strain curve, right? If you guys wish to revise, you can go to the last week's, which is last Friday. Okay, you can browse through them, and under one of them I had discussed stress strain curve as well for you guys. So today under this chapter we are going to be doing a different topic. Okay, elastic potential energy. Okay, it's also very interesting topic. Okay, I hope you will find it interesting. See over here, I will talk about two forces in this one. Okay, two forces. So what are they? Let's say one is deforming force. Before we begin, right? So you need to know what these are. The another one is deforming force. The another one is restoring force. Okay, hang on. Okay, you'll find it very interesting. Now listen carefully. Now what is deforming force? Right. So let's say, for example, right? Let's say, let me draw over here. You have a cylinder, okay, or a rod, whatever you want to call it, all right, and let's say this is the cross-sectional area of that rod, right? And what I am doing, I am applying a force at this cross-section, and what I am trying to do, I am trying to pull this rod. The rod will, let's say, try to extend, right? If it has some elasticity, it will try to extend. Or you can, if you want, you can imagine by taking a simpler example. Let's say we have a rubber band, right? A rubber band, if I try to apply force like this, what will happen? The rubber band elongates. Now what kind of force is that one? That force is called deforming force. Why? Because we are trying to deform the object, right? We are trying to change the configuration of that object, isn't it? Initially the rubber band was, let's say, like this. I am trying to pull it. That is deforming force. Now what is restoring force then? What is restoring force? Let's say I pulled the rubber band up to elastic limit. Why only up to elastic limit? Because if you pull it greater than, if you pull up to, let's say, a dimension greater than your elastic limit, then if you leave, then if you remove that deforming force, what will happen? There will be permanent plastic deformation in that rubber band, which means it won't be able to come back to original dimension, the way it was before we started everything, right? So restoring force tries to bring the rubber band to its original dimension. So let's say we have not exceeded the elastic limit. Even in this topic also, we are not going to be exceeding the elastic limit, all up to the elastic limit. Okay, so we have applied some deforming force, and let's say I leave it suddenly. What will happen? That rubber band will come back to its original length. That is because of restoring force. Okay, that is because of restoring force. So you guys can remember. Okay, so you can remember it like this. So let's say work done by deforming force. Okay, work done by deforming force, right, is what can we say? It is against the restoring force, isn't it? That work done, the deforming force is obviously, it will be in the opposite direction, right? Let's say, for example, if the restoring force was pulling that rubber band towards inside, then the deforming force was pulling the rubber band towards outside. So it is against the restoring force. You can remember it like this. And this work done, right, it will get stored. It will get stored as elastic. It will get stored as elastic potential energy. Okay, elastic potential energy. So just find the work done, and that would be equal to your elastic potential energy. Okay. All right. So let me draw this diagram again for you guys. So what I was just saying, right? We had applied a force F to stretch. This is not a rubber band, obviously. This is a rod. We're trying to stretch this rod, okay, so towards some distance. And if we suddenly leave that force, and if it returns to its original dimension, that means the restoring force is in full play. Okay, that means that we have not crossed the elastic limit. That means the Hooke's law is still valid. Okay, that means there is no plastic deformation also. See, multiple things are connected over here. So let me draw a new diagram for you guys. See over here. Right, and let's say I'm applying a force F. So what would happen? The rod will elongate, right? So let's say the rod has elongated up to over here. Okay, elongated up to here. Let's say how much? Let's say by distance x. Okay, by distance x, and obviously we are applying that force F as well, right? The force F is still active. Now, due to this force F, this rod will, let's say, undergo another additional deformation or additional elongation equal to delta x. Okay, so additional dx, let me call it. It will elongate. So what can I say the work done is? Small work done. What can I write it as? It would be nothing but f dx, isn't it? The work done, force and the displacement are in the same direction. This would be it. And if you remember from Hooke's law, we had talked about Young's modulus. So what will be Young's modulus is stress upon strain, isn't it? Stress upon strain. So please remember this formula. It would come in handy when we do the next questions, right? So what would be stress over here? Remember, over cross-sectional area A, this force F is acting, right? So what will be the stress? Stress would be nothing but F upon A, right? F upon A. And strain meaning change in dimension upon original dimension. Or here in this case we are changing the length. So change in length upon original length. So what was the change in length? X only, right? Original length was how much? Let's say we call it the original length as, we can use capital L also, or we can write, let's say, L naught. I'm writing. So original length is L naught. And this is your Young's modulus. So from here, what will this become? See, F L naught over AX. Right? So can you find the expression for F from here? F will be what? Take these terms to that side. So it becomes AY by L into X. See, AY by L into X. See, A here, L here, or in this case, L is L naught. Alright, this is pretty similar to a spring, isn't it? We were talking about spring just a few moments ago, that F was equal to how much? Kx, and here F is equal to something into X, and this something is a constant, isn't it? A, Young's modulus and original length, they are constants. And also remember, during this elongation, there has been no change in cross-sectional area. That also has been perfectly made clear to you at the beginning of the question. Alright, so there is only change in the length, not in the area. So you can substitute this term over here, right? Substitute it. You can, if you want, you can take it as K also, or I am taking it pretty much the same thing. So substitute it. What does it become? AY by L naught x dx. X dx. Now what we will do, we are going to integrate both sides, right? Integrate. See, integration we are going to do. dw is equal to AY by L naught x dx. Okay? We are going to do integration, and but remember, I just now told you these are constants, so the constant will come out of the integration sign. So I will directly write the sign over here. Okay? So initially at x equal to 0, right? At x equal to 0, there was no work done, so w is equal to 0. Then finally, let's say if the final elongation is x only, the total elongation is x. So what will be the total work done? That is w we are supposed to find, right? So what will this become? X dx, integral x dx, right? That is x square by 2. This also we did, I think 1 or 2 sessions earlier to this. Integral x dx is x square by 2. Then x square by 2, put the limits from 0 to x. That would become, see over here, this is w, so w minus 0, right? Putting the limits. Now here, a y by L naught, again put the limit, it becomes x square by 2 minus 0. Why 0? When you substitute 0, the value becomes 0. X square by 2 becomes 0. So just, what does this become exactly? If you see over here, this is the expression for your elastic potential energy. Okay? This W, right? W is your, let me write over here, elastic potential energy. Right? And what does the expression become exactly? AY by L naught into x square by 2, or half AY by L naught into x square, right? But just now you can see over there, AY by L naught into x. What does that term be equal to? It is equal to f only, right? So this expression becomes half into f into x. Okay? Half into f into x. All right? Now let me erase these terms. See carefully what we are going to do. I am going to give you another expression for elastic potential energy. Another expression. How exactly? See? If you want, I can erase this one also. This was your energy, right? So let me write it as U only, right? Half into F into X. I'm again repeating, this F was your deforming force, X was the elongation. Now what I'm doing, I am dividing it by, let's say I'm dividing it by A. That you have to multiply it by A as well, isn't it? I multiplied it by A. Then, let's say I'm dividing it by L also. Then I have to multiply by L as well, isn't it? If you divide by a quantity, you have to multiply it by the same quantity so that the original value does not change. So what does this become? See? Now what are these equal to? If you see over here, this is half. What was F upon A? We wrote just now, just a few moments earlier, right? F upon A was what exactly? It is stress, right? X upon L, What was that equal to? Or if you want, we had written L naught, isn't it? So I will write the same expression upon L naught, because the original length was L naught, right? And what was x upon L naught? That was your strain, right? And what is this? A into L naught is the area of cross section. L naught is the original total length. So we can call it as volume, right? This one is your volume. So from here you are getting a new expression or a new term, right? That is energy density. And also remember, in NEET, so many questions can come from your dimensions also, right? So let's say they can ask, what is the dimension for elastic potential energy? It would be dimension of energy, right? The SI unit would be joule, so dimensions would be for joule. And here for energy density, so what is the formula? It is total elastic potential energy per unit volume. So you have to divide it by volume. And what will this become? Bring this volume over here, that's all, isn't it? Bring volume over there, so what will that become? Half into stress into strain. Okay, half into stress into strain. So please remember these two expressions. This was for your energy density, and this one was for your elastic potential energy. Okay. Yeah, good afternoon. Good afternoon, Janak. Elastic potential energy. So let's do some questions. Let's see what this question is asking us. See here. See over here. What are they saying? A wire of length 4 meter. So original length is given, right? That L naught is given, stretched through 2 mm. The total elongation is also given. Stretched through. Okay. Pulling it. Stretched through 2 mm. Young's modulus is given. So Y is given. And the energy density they are asking. Energy density they are asking. What was the formula for energy density? Half into stress into strain. Stress into strain, right? Half into stress into strain, right? But why didn't I write stress over here? Because remember, no forces have been given. For our derivation I had taken that force F, but here nothing is given. Nothing is given, right? Strain is given. Strain we can find out. So how will you do this question? You have to use the formula for Young's modulus, right? So what was Young's modulus? This formula comes in handy so many times, isn't it? Stress upon strain. So find stress from here. Stress is nothing but strain into Young's modulus, strain into Y. So here again you will write strain into Y. Strain into Y. Strain into strain will become strain square, and then you have Young's modulus Y. That's all. Okay, see how I modified that, how I modified this formula. It became this formula. It was the same formula, right? So that's it. So substitute over here. Half into Young's modulus is how much? 10 raised to the power 11, isn't it? And then strain, what is strain is equal to change in dimension by original dimension, x upon L, right? X is how much? 2 mm. And you have to, in physics, you have to use SI unit while doing multiplication and division. So 2 mm in meter, it becomes 2 into 10 power minus 3, isn't it? Upon original length. Original length is how much? 4 meter, right? Just do simple multiplication. So what does this become? See, 2 and 4 get cancelled, it becomes 2. Then 2 square will become 4. So, and this is 10 power 11. So 10 power 11 multiplied by 2 into 4. 10 power minus 3, this one, right? And 10 power minus 3 whole square, 10 power minus 6. What does this become? 10 power 5. And this is 8, right? 2 into 2, 10 power 6, 5 upon 8, 10 power 5 upon 8. Now from here you can take a 10, let's say like a lone, right? So it becomes 10 upon 8 into 10 to the power 4, right? And what will be the unit? As I said, please remember the SI unit. energy density is elastic potential energy upon volume. So elastic potential energy is joule upon volume. Volume unit is what? Meter cube. So the answer to this one would be in joule per meter cube. But anyway, you don't have to worry about the units because here they had simply written in SI units. Alright, so just calculate this, 10 upon 8, you would get it as 1.25. Okay, so the answer to this one would be this one, right? 1.25 into 10 to the power 4. Okay. See, let's do a similar question, just like that one, right? Everything, the values and everything are the same. But here they are asking something else. See, read the question. What are they saying? Then the stress acting on the wire. The stress acting on the wire, we found out just earlier, isn't it? Stress, what was that equal to? Stress is equal to strain into Young's modulus. So Young's modulus into strain, isn't it? Strain was how much? X upon L or delta L upon L, or we can say X upon L naught, the variables that I had used. So just substitute the values. Young's modulus was what? 10 to the power 11. Strain is okay, 2 mm by original length 4 meter. So that's it. You just have to solve then. 10 power 11, that is 10 power 8 upon 2. 10 power 8 upon 2, and this becomes, take 10 as a lone from this 10 power 8, and what remains is 10 power 7. 10 by 2 is how much? 5. So 5 into 10 raised to the power 7. Right? And once again, let me write the unit as well, right? Please solve it, huh? And this becomes, the unit will be in Pascal. Okay? The unit will be in Pascal. If you want, you can write Pascal over here, or here in the question itself, it has been written Pascal. Alright? Yes, Akansha, the answer would be 1.25. Yeah. Very well. See, read this question as well. Please read this question. If you want, you can take it as a homework, right? The same question, the same values, but what are you supposed to find? You are supposed to find elastic potential energy stored in the wire. Okay, just a minute. Yeah, sorry about that. Yeah, you have to supposed to find elastic potential energy stored in the wire, and we have just now derived the formula, right? If you know the energy density, you can find elastic potential energy as well. What would that be equal to? Energy density? Elastic potential energy is energy density into volume, isn't it? Into volume, and what was volume equal to? A into L naught, right? What we had written earlier, the area of cross section into the length. And if you see in the previous questions, this there was no need for cross sectional area, right? See here, read the question. There's no term as cross sectional area. Then here also, but here you have this information provided. Cross sectional area of the wire has been given to you. Why? Because for using this. Okay, so I hope this is pretty much clear, isn't it? I had used this expression, right? This expression. If you want to find energy, it is nothing but energy density into volume. Energy density into volume. Okay, so please solve it, right? Please solve it. Very simple, right? You will get the answer as 0.1 joule. All right. Put area as 2 millimeter square. Length, original length is given 4 meter. Substitute and put the energy density as well from the previous question. Substitute, you will get the answer. Okay. Moving on, we are moving on to our next topic, nuclei, right? And under nuclei, what are the things we have done so far? If you remember, we had discussed about the density of nucleus, right? It remaining constant, isn't it? We had done some questions, and I believe the first questions are on that one only, right? If you remember, if you want, you can revise once again, right? The radius of nucleus of let's say mass number A, right, of mass number A. So mass number is given to you. And what is mass number? Total number of nucleons in the nucleus. So mass number A, the radius will be expressed as R is equal to R naught A to the power 1 by 3, right, where A is your mass number and R naught is a constant. Okay, so R naught, it is equal to 1.2 Fermi. Okay, Fermi meaning 10 to the power minus 15 meter, a very small value. This is your R naught. And what about volume of nucleus? Volume of nucleus would be taking the nucleus as a sphere of radius r. The volume would be 4 by 3 pi r cube. So pi r cube, right? So r cube, it would be proportional to what exactly? R cube would be proportional to A, right? Take cube both sides, A 1 by 3 whole cube, 1 by 3 into 3 get cancelled out, so it becomes A. So volume of nucleus is proportional to A, your mass number. And what about density of nucleus? Density of nucleus is mass upon volume. So mass is, let's say, A upon volume. But just now we told that volume is proportional to A. So A upon something that is proportional to A. So A and A will get cancelled out, right? And what would remain is a constant, some constant. Okay, this constant also we had derived over there. So density of nucleus, it is equal to constant. Okay, so if you want, I can write down, it is A by volume 4 by 3 pi r cube, and this would be equal to constant. Okay, but I believe the coming questions with this just with this information that the density remains constant, you will be able to do those questions. Let's see what the questions are, right? Very simple questions. See the first question. Read this one. The ratio of nuclear density of this nucleus and that nucleus. Just now I told you, right? The nuclear density, the density of nucleus remains constant for any mass number, for any atom. So the nuclear density is going to remain the same. So ratio would be 1:1, isn't it? Very simple, this one. Let's do a similar one. See this one. Density of gold nucleus is given. And what are they asking? Find the density of silver nucleus, right? So nucleus has changed, but the mass number is also changed, but the density, it will remain the same. So what about the density of silver nucleus? That density, that would be nothing but x only, right? Because this one's density is x. Okay? So it's very simple. Now see this question, right? This question is a little different. See over here. Two nucleus are given. Two different nucleus are given. They have different mass number. They will have different radii, but they will have the same density. But here they are not asking about density, isn't it? So read the question. If radius of aluminium nucleus is R, Al, then the radius of this nucleus, tellurium, right? What would this be? So let's say, what about this nucleus? What can you write it as? Let's say this one's radius is R1, or what they have written, right? RAL. And this one's radius is RTE, the same terminology I am using to write. So what can we write this radius as to be equal to? Let's write over here. See, it's a very simple question, this one also. R aluminium can be written as equal to R naught A to the power 1 by 3. Now what is A over here? Mass number. Mass number is which term? This term, the one written over there. The quantity written below is your atomic number and mass number. So mass number is 27, right? So A to the power 1 by 3, right? What will this become? Solve it. 27 cube root is 3. So 3 R naught. Okay. Now what about this one, TE? Let's write for that one also. RTE is equal to same expression R naught. What is the mass number for this one? 125. So 125 whole to the power 1 by 3. And that one will become, see, 5 cube, 125 is 3 and 3 will get cancelled. So it is 5 R naught. Okay. Pretty simple this one was. If you know that relation, you would be able to do this question. So take the ratio now. Let's take the ratio. So RTE by R aluminium, it is equal to this upon this, right? So 5 R naught by 3 R naught. Okay. R naught get cancelled out. What remains is 5 by 3. Take this RAL to that side, right? So RTE, it will become 5 by 3 RAL, right? Which are the options? That one says this one. Okay, very simple this one was. Okay, so please remember this formula, right? Please remember this formula. So many questions, some question or the other would come in your NEET as well, right? Or they could ask from this one, find the ratio of their volume, or they can ask find the ratio of their densities. Moving on. See, now we have entered another topic, a different topic, right? Someone which we had not covered so far. Radioactive, a reaction involving radioactivity, right? So about this radioactivity, some small snippets I will share with you guys. Right? We are not going very much in detail. We are just following NCERT, right? So for example, the one decay they can ask is about alpha decay. Alpha decay, that means the helium nucleus is emitted. Okay, helium, so 2H4 nucleus is emitted. Now because of this, what would happen to the atomic number and mass number of the other nucleus that is coming along with this helium, right? So that one, we are going to be talking about that one. For example, what I am trying to tell you, if you read this question, right, what are they saying in this question? If you read, they have given a radioactive reaction, alpha and beta particles are emitted. This is, let's say, the parent nucleus, this is the daughter nucleus. So along with it, you have alpha and beta particles that are emitted. Okay. So due to this alpha decay, we will say Z decreases by 2. Why Z decreases by 2? Because helium has an atomic number 2. It is being emitted along with that other nucleus. And mass number, it decreases by 4. Okay. Then the another one is, let's say, beta decay. In beta decay, you have two various decays. So one we are going to be talking about. Okay. The beta, this beta particle is emitted. Okay. This one, this particle is emitted. All right. This particle is emitted. So what does that mean? What will Z decrease by? If you see over here, this particle has the same charge as the charge on an electron. So that means the Z of that other nucleus, right? You can say Z increases by 1. Z increases. Why? Because this this particle with a -1 as it's this number, right, is emitted along with it. Now what about mass number? Mass number remains the same. With this much information, you can you would be able to do that question. So let's see. And you have another decay as well. Okay, that is gamma decay. That is not being asked in our question. And also remember, this is beta minus decay. There is also another beta plus decay as well, but that is not in the question. So in gamma decay, what happens? A photon of high energy is emitted. Photon of high energy is emitted. All right. So that means there will be no change in Z or A. of the parent nucleus, right? That means Z and A, right? Z will remain the same and A will remain the same. All right, so let's see the question, what that question was saying. You see, this was our nucleus, right? Initially this was, and this becomes Y, right? So X atomic number is 92, it reduces to 88, right? And the mass number 232 becomes 220. Some alpha particles are emitted and some beta minus particles are also emitted. But if you remember, in which decay did I talk about change in mass number? If you remember, mass number was changing not in this one, but in this one only in alpha decay, right? And for each alpha particle that is emitted, or helium, this nucleus it is emitted, atomic number will decrease by 4. For one alpha particle, atomic number decreases by 4. But here if you see, atomic number has decreased by how much? See, do the subtraction, 232 minus 220, right? This much it has decreased, you divide it by 4 and you will get, what will you get? Number of alpha particles. So what will this become? See, 12 by 4, that is equal to 3, right? So the answer would be 3. So from this much itself, we have solved the question. We have solved it, right? But they are asking a few other things as well, right? Isn't it? Let's see. We can find the beta minus particles as well from this one, isn't it? How? See, what was the original atomic number? 92. And due to one alpha decay, right? Due to one alpha decay, Z decreases by 2. But here, how many alpha particles were emitted? 3. So the Z decreases by 2 for each one of them. So total decrease would be how much? Decrease meaning, I am putting minus sign, minus 3 times of 2. For each alpha particle, it decreases by 2. So minus 3 into 2. Then for beta minus particle, Z increases or decreases? It increases. That's what I wrote, right? Z increases by 1 for one beta minus particle. But here we don't know how many beta minus particle. So let's say I'm calling it as N beta. Okay, N beta, and Z will increase. So I will put the plus sign, and this 92 finally becomes what value? See over here, 92 becomes 88, that's Z. So put it equal to 88. Don't worry, I'll give you another question as well. I hope this was very basic, right? So simple subtraction, right? 92 minus 6 is how much? 86. 86. This N beta would become how much? So number of beta minus particle has to be 2, right? So that the sum is 88. Although beta minus particle they did not ask even, right? Yeah, in beta decay mass number remains same. Yes, mass number, there will be no change in mass number, which happens only in alpha decay. All right, anyway, let's do a similar question. See this question as well. See this question, 90, this becomes, right, when the nucleus of this one disintegrates to give one nucleus of Pb, right? You don't need to memorize their names, etc., but it's a simple calculation you need to know. The number of alpha and beta minus particles are. Alpha and beta minus particle they are asking. So very simply, we will do employ the very exact same method what we used in the previous question, right? Number of alpha particle, how will we find? Find the decrease in mass number, right? So number of alpha particle. Find the decrease is how much? 234. Use the same thing, 234 minus 206 upon 4. Okay, so what is this way? 28. 28 upon 4. That is 7, right? And what about beta particle? The same thing. Initially it was 90, then 7 alpha particles are emitted. So atomic number will decrease by 7 into 2. Then let's say N beta minus particles are emitted. So atomic number will increase by N beta. So plus N beta. And finally it is equal to, what is the final atomic number? Final atomic number is 82, right? So we will write 82 over here. So just have to solve it. See, this is 14. 90 minus 14 is how much? 76. So N beta will become 82 minus 76. That is 6. Pretty simple this one was. So if you can see, number of alpha is 7, beta is 6. So which one would be the correct answer? This one, right? In fact, actually there was no need to do this beta calculation as well, right? Just by solving this n alpha is 7, you could have ticked the correct answer, right? If you see only one option is matching, alpha has to be 7 only. So this would be the correct answer. All right? Very well. So let's finish our today's lecture with the last topic, atoms, right? Some basic questions this one would be having. Let's see over here. See, very, very basic question, right? The value of first Bohr radius A0. See, for this one, you need to remember the expressions for the radius of nth orbit, the velocity of electron in nth orbit of which atom? Hydrogen atom, right? So we are talking about hydrogen atom. Okay, we are talking about hydrogen atom, and perhaps some other day I will show you the derivation for this one also. It's a very interesting derivation, right? So for nth, right, for nth orbit, the radius, it is nothing but 0.529 angstrom, right, n square by z. This is the radius, right? And what about the velocity? The velocity is 2.2 into 10 to the power 8 centimeter per second into z by n. Okay? So how will you remember? This one is n square by z and this is z by n. If you want, this expression can also be written as, right, c by 137 into z by n. Z is your atomic number, but I always prefer to use this, this expression. All right. So if you see, for first orbit, right? First orbit means n is equal to 1, and for hydrogen atom we are talking about, so z is equal to 1. So what will be the radius? So R1 they are talking about, right? So 0.529 angstrom, isn't it? This is what I written over there, into n square by z. So 1 square by 1, 1 only. So this is your answer. You just have to check which one it matches with, right? If you see, angstrom is 10 raised to the power minus 10, right? And this you can write it as 5.29 into 10 to the power minus 1 into 10 raised to the power minus 10, right? So what does this become? If you see over here, it matches with 2, isn't it? Minus 1 into minus 10 becomes minus 11, 5.29 into 10 raised to the power minus 11, and the unit is meter. SI unit is in meter. All right. Moving on, and also remember the expression for energy as well, right? Energy, what was that one? Let me, if you want, you can write, let me write that one also. Energy is minus 13.6 electron volt. We are writing for hydrogen atom, right? For hydrogen atom, Z will be 1. Put Z is equal to 1. Everything else will remain the same. Into Z square by N square. Okay? Z square by N square. Now see this question, velocity. It's also pretty simple, right? We just now we wrote the expression, isn't it? Vn is equal to, what would be the correct answer? This one? This was directly written from there. And if we want in meter per second, and remember for first orbit means n equal to 1, z equal to 1. Okay? In this one, z equal to 1, n equal to 1, this would be the answer. And you can also remember it like this, 2.2 into 10 to the power 6 meter per second. All right? Very well. Now let me, before we end our session for today, let me give one more homework for you guys. You guys can check, right? See this one. This one would be your homework for today. The energy of electron in first orbit of hydrogen atom, n equal to 1, z equal to 1. That energy can be written as what exactly? If you remember, we had also talked about Rydberg's constant, right? While writing the expression for wavelength, for transition from one orbit to another orbit, we have used this Rydberg's constant R, H and C you already know. So try this question, okay? The correct answer would be 4. If you want, you guys can try. Yes, Akansha, you can please try solving the momentum booster. It has lots of questions from lots of topics. It would be of good help. All right, students, I guess that's it for today, and I hope you had a great time. Keep watching and keep practicing. Thank you.